So we're going to look at Chapter 7 today, Reactions in Aqueous Solution. Some of the reactions that occur in aqueous solution are the most important types, particularly since all biochemical reactions, those that occur in our body, are aqueous based. In other words, they only occur because the reactants are dissolved in water. So let's get started with share the PowerPoints. And there we go. So I'm going to move along with the PowerPoints, and at a couple of locations in here, I'm going to stop and go to an external video. The video is embedded in the PowerPoints, but for some reason, the quality that comes through on the recording when I process the Zoom recording is not very good. It's better if I go out and call up the video separate from the PowerPoints. So that's what I'm going to do, just to improve quality. Let's see, slideshow, here we go. All right. So we've gone through chapter 4, 5, and then we skip chapter 8, and then we come back to chapter 6 and learn how to balance equations, learn a method of balancing equations. There's actually more than one. And depending on what type of equation you're trying to balance, sometimes one works better than the other. And hopefully I'll be able to show you one of those little tricks at the end when we get into, I can call up, stop the slides and then show you a couple of equation balancing tricks. Okay, so we're going to look at reactions in aqueous solution today, which is chapter 7 in your book. All right. What are the driving forces? Now, this is a descriptive journey that we're on here. And sometimes it's helpful to have some intuition, develop some intuition for when a reaction is going to occur and what drives a reaction to occur. Sorry for the diversion. I've got 15 cats, and there's always one of them every day that's got a hairball they have to throw up. I just want to make sure they don't throw up on my books. Okay, back to the topic. We're going to look at 4 driving forces that favor chemical change. They're not the only ones, but they're the major ones. Whenever a solid is formed in a chemical reaction, that tends to drive the reaction forward. And if you look at it this way, say you have 2 reactants. Let's not do it that way. This way. And they're in aqueous solution. And one of the products is a solid. So think about the reaction. The reaction occurs between A and B because they are in aqueous solution. Many reactions that we observe in aqueous solution will not occur if they're not dissolved, because there's no intimate association between A and B unless they're in the same solution. So what happens when you make a solid? Well, in many cases, reactions can go forward and reverse. Right? Reaction can go backwards. But if you form a solid, you're removing that product from the potential reverse reaction. It just drops out of the story, becomes unavailable. So that tends to drive the reaction that way. It won't go back the other way. So formation of a solid is one driving force for a chemical reaction. Strange as it may seem, formation of water can be a driving force. And that's something that occurs typically in acid-base reactions. So if you have an acid in aqueous solution and you react it with a base in aqueous solution, well, the acid is defined by this proton that can dissociate. And the base, in this case, many bases have hydroxyls in their nature, in their structure. So the OH and the H combine to make water. And they also make sodium chloride. But since sodium chloride is soluble, it stays in solution. So why would formation of water drive a reaction? Well, the fact of the matter is, in this solution, you don't have these complete compounds. In fact, what you have is the independent ions. In solution, right? And you still have sodium and chlorine over here in solution, just like that. Well, the reaction that you're interested in is really the one between protons and hydroxyls. That makes water. All right. Now, which side does the reaction prefer? It prefers the water side, because the reverse reaction is the tendency toward going backwards toward these ions, if you have water, is almost nothing. So the formation of water tends to drive the reaction because that's where the reactants want to be. They don't want to be over here, they want to be there. So if you form water, then any reaction in which water is formed tends to drive the reaction in that direction. Now, we need a further discussion, a more complete discussion of this will occur when we talk about acids and bases. Then we'll get into some more details, and it should become, should become obvious at that point. But for now, formation of water is a driving force. Transfer of electrons is also a force that drives reactions. And I might add, in some reactions, you could get two or more of these occurring at the same time. So when we talk about transfer of electrons, the authors of your book, to simplify the matter, focus in on the transfer of electrons from metals to nonmetals. Right? So if we have sodium metal and chlorine gas, in order to produce sodium chloride, you have to transfer electrons from the sodium to the chlorine. And if the difference in pull for electrons is great enough, chlorine has a very strong attraction for electrons. We call it electronegativity. Sodium doesn't have that strong attraction, so it gives up electrons very easily. When they come into contact with one another, then the transfer of electrons drives the reaction in that direction. Another driving force is the formation of gas. And it's for a similar reason, the formation of gas drives a reaction as the formation of a solid. Because if you have reactants in aqueous solution, and then you form a gas, where's the gas going? It's going out, away from the reaction environment, which tends to pull the reaction toward the formation of the gas. Okay, those are four main driving forces for chemical change to occur. And at this point, I'm going to stop the share and pull up the video separate from the slides so that we'll get a better quality. It may not be a better picture for us, but it tends to record better. So I'm going to stop this share, and then I'm going to go and share the video that was just referenced there, if I can find it. I think it's here. Yeah, this is it. Okay. It's a long video, but it's entertaining.
So in the reactions we've seen so far then, we mix chemicals together and we know that a reaction has taken place because we get a change of colour. So there are lots of other ways that a chemical reaction can show up. And one way is called a change of state. So the state of something just means whether it's a solid or liquid or gas. So if something turns from a solid to a liquid or from a gas to a solid, then it's changed state. So let me show you an example of a chemical reaction that involves a change of state. So I'm going to use these two liquids. I have a red liquid and a colourless liquid. What I'm going to do is to pour the colourless liquid onto the red liquid very carefully and try to make two layers. So what I want to happen is for the colourless liquid to be floating on top of the red liquid in separate layers so they don't mix. So that's worked quite well. So what I've got now is one liquid floating on top of another, and where they meet, they undergo a chemical reaction. They're actually making a solid. A solid material is formed where the two liquids meet. What I can do is to fetch out some of this solid material. And as I pull it out of the beaker, of course, it allows the two liquids to meet each other again, and so they react again to form more of this solid. So if I'm careful, so as I wind, I'm pulling up this material, and it allows the two liquids to meet again, and it forms more of this material. And this substance that's being formed is actually nylon. So we're making nylon as I speak. And if I'm careful, I'd be able to just keep on turning this and making this long thread of nylon, at least until we run out of solutions. Okay, so that's an example then of a chemical reaction that involves a change of state. So let's have a look at another reaction that involves a change of state. And for this, I'd like a volunteer, please. Who would like to volunteer? You're very keen. Come on down. Let's have a big hand for a volunteer. Who would like to stand there? Let's pop those on. What's your name? Dylan. All right, Dylan, if you stand just there, we're going to do some chemistry and we're going to make it a solid. Right? I'm going to start off with a flask that contains a solution of silver nitrate, and I'm going to add a little bit of ammonia. When I add the ammonia, you see that it's forming a sort of brown colour. We'll keep on adding the ammonia. And in a minute, that brown colour should disappear. Oh, it's disappeared, isn't it? Now what I'm going to do is to add some sodium hydroxide. That's now formed a sort of very dark brown, almost a black material. So now I'm going to add more ammonia. And again, I'm going to add ammonia until the liquid goes back to being colourless. Let's take a moment or two. There we go. And then finally, I'm going to add some glucose. So there's the glucose. I'm going to put the lid on, put a clip on. I'm going to give it to you, Dylan. I want you to hold that. Now I want to give it a really good shake. That's it, really hard shake, that's good. That's it, keep shaking. That's it. So what's happening inside this flask now is there is a chemical reaction taking place and it's forming a solid. And the actual material that it's forming is silver. We're making pure silver metal. Keep shaking. It takes about 3/4 of an hour, is that okay? It does actually take a minute or two, but the harder you shake, the better it works. So keep shaking, don't drop it though. Okay. So metal, silver metal is being formed sort of atom by atom, and you can see it's all going quite black. That's because very finely divided silver is actually black in color. What we're hoping is going to happen over the next minute or so is that those particles of silver will start to stick to the walls of the flask. And as they build up, we should see silver metal in the form of a mirror building up on the inside of the flask. And you're all seeing those sort of decorations that you get at Christmas, those spheres that are shiny, and they're made using this chemical reaction. Little balls of glass, and the inside is coated with silver using this kind of chemistry. Doing really well. Okay, so have a quick look. Almost there, keep going a little bit longer. So looking a little bit dark. Excellent. All right, give it back to you then. Right, I'm going to take the clip off. Take out the stopper, just wash that off. And I'm going to pour out the remaining chemicals. And then I'm going to rinse this out with distilled water. Rinse it out a second time. Rinse out a third time. There we go. I'm just going to put the hat on, dry this off. And put the clip back on. And if you want to just get a little polish, there we go. If you like to hold it up by the neck, that's it. And if we bring a camera in and have a look at this, and we've got a lovely silver mirror. There we go. Okay, just stand there. Okay, what I'm going to do is give that to you as a souvenir to take home, and you're back to your seat. Let's have a hand for a volunteer. So that's an example of a chemical reaction that produces a change of state. I want to show you another example of a chemical reaction. Again, this is going to go from being a liquid to being a solid. So in this flask, I have a solution of sodium acetate. And this sodium acetate is a liquid, as you can see, but it would very much like to be a solid. It would like to turn into a crystal. But it needs a sort of an excuse to get going. And the excuse is going to be some little crystals of solid sodium acetate in this dish. So watch what happens as I pour the liquid onto the crystals. I think you can see there the liquid, as soon as it touches the crystals, it's turning into a solid. And with a bit of luck, we can make a sort of chemical sculpture. Seems to be working. Okay, so that's a sort of sodium acetate sculpture. Now, oddly enough, this actually has a practical application, and this is the practical application. This is something called a hand warmer, and it's a plastic pouch, and it contains exactly the same liquid as in this flask. It's a solution of sodium acetate, and it would like to turn into a solid, it would like to turn into a crystal, but it needs an excuse to get going. And the excuse is this little metal disc, and if I just flip this disc backwards and forwards, that should be enough just to start the crystallization off, and there it is. And we can see the liquid turning into a solid. And as it does so, it's actually getting warm. So it's actually giving off heat. And there it is, it's turned entirely into crystals. It's become quite warm in the process. I can put that inside my glove and keep my hands warm for half an hour or so. And then I can take this and put it into boiling water for a couple of minutes. The crystals will turn back into a liquid, I can allow it to cool, and they'll stay as a liquid. It will stay like that for weeks or months until I'm ready to use it again. I can use it thousands of times. Okay, so that's sodium acetate, a sort of chemical sculpture. I'm going to show you now another way to make a chemical sculpture. And Chris has been preparing this. This beaker contains a mixture of para-nitroacetanilide and sulfuric acid. And Chris has been warming it up. And when it's hot enough, it will undergo a reaction in which this liquid will turn into a solid. This makes quite a bit of smoke, so we've got this special hood that will suck away the smoke from the reaction. So here it goes. Okay, so that's a chemical reaction that involves a change of state. So
all right, so let me stop this share and go back to our slides. Here we go. Oh, I got another one. Right, well, discussion first and then I'll show you another video. And that change of state for the demonstrations that were done in the previous video were focused primarily on changing from a liquid to a solid. But a change of state could be like one of the driving forces we mentioned earlier from a liquid to a gas. Precipitation reaction. This is one where you change, you add one liquid to another, and you can produce a solid. And the formation of nylon that the demonstration showed you in the beginning when it was rolled up on the spool technically could be called a precipitation reaction, but it's really an organic reaction that produces a polymer. Nylon is a very long chain molecule. In fact, it can have infinite length, and that trait has been capitalized for let's see, the inventor, which escapes me now. I can't remember the name of the inventor, but they worked for DuPont, a chemical company, and produced nylon. And that one invention, which was patented by DuPont, produced millions, perhaps even billions of dollars of revenue for that company. Just that one discovery. Okay, so the solid is called a precipitate. And in this case, we see that we've added this colored but transparent liquid to this liquid, which was transparent but colorless. And the reaction that occurred produced this solid. Now, the video that's coming up will explain what this reaction, what the reactants are, and the product of the reaction. All right, so I'm going to stop that share and go to the external video. Let's see if I can remember where it is. Here it is. Okay.
What I have here is two Erlenmeyer flasks. One has lead nitrate solids in the bottom, and one has potassium iodide solid or salts on the bottom. I'm going to make a solution an aqueous solution with these. So I'm going to make aqueous lead nitrate here. Mixing, you can see that it makes a solution. It does dissolve. It is definitely aqueous. And same thing with the potassium iodide. Where I'll make as much of a mess. It's the Ki, adding some water. Also making an aqueous solution. And both of these solutions, or both of these salts, are soluble in water. So they stir. And I have two aqueous solutions. You can see through them, and you can see the solids are now been dissolved. Okay. Now, interesting enough, lead nitrate is made of the nitrate ion. The nitrate ion is NO3 minus 1, and anything combined with the nitrate ion is soluble because the nitrate ion, NO3, is 4 atoms stretched, and you have a negative 1 stretched over 4 atoms, so its charge density is very low. So it doesn't attract other ions in a crystal as strong as others. So its lattice energy is lower, and it's easy for water to pull apart the ion and have those molecule ion attractions that make this a possibility. Same thing with Ki. You have potassium iodide, you have Ki ions that are free in this aqueous solution, and the K is +1. The +1 ions are a big ion, and they are spectators for most types of reactions because they have a +1 over a large area as well. And the iodine, like most halides, are also soluble because they're a -1. It's also a big ion. There's some exceptions with those, and we're going to see that one right here. So I'm going to pour these together and take 2 aqueous solutions and see if a precipitate results. Now, precipitate is when a solid comes out of the solution because we're going to do a double replacement, or something called a metathesis reaction. Lead +2 from this beaker is going to attract and hook up with the iodine ion to make PbI2, or lead-2 iodide. And that is going to create a precipitate because the lead iodine prefers itself more, or attracts itself more, than water. So let's do that. Here we go. Very brilliant reaction. You see that as pretty, very pretty yellow precipitates. A lot of yellow lead paints have been known to be yellow, and also a problem. So there you go. There's your precipitate. And it's a precipitate because I know that I cannot see through the solution anymore. And if we let this settle for a while, we'll get something like this. This is a reaction I did about an hour or so ago. And you can see here that the clear solution is the potassium nitrate ions, or potassium and nitrate ions, and the solids are at the bottom. That's settled up at the bottom. All right? So there is your precipitating reaction. What I have here is 2 Erlenmeyer flasks.
Okay.
One has...
We don't need to see that again. All right. That, let me reshare the slides here. Okay, this reaction here is actually different than the one that he was showing us. But the illustration is the same. Formed a solid by that interaction. And he used some big words in there like metathesis and lattice energy. So don't worry about that. He's trying to explain why things are happening. And all I wanted you to do was just see that solids can form from 2 aqueous solutions. Now, we could balance this equation, right? As long as we write the compounds correctly, which we have here, and the products here. I was listening to what he was saying and wrote the reactants and products. And then to balance, we need 2 iodines there, and we need 2 potassiums as a result. So now we have 2 potassiums, we have 2 nitrates, we have 1 lead, and we have 2 iodines. So that equation is balanced. All right. Let me see. I got something in the way here. Let me see if I can move it out of the way so I can see what I'm doing. So you may have often heard the expression, water is the universal solvent. Well, that's a bit of an exaggeration. Water, excuse me, water does dissolve a great many substances in the universe. And it's particularly important for chemical reactions involving living systems as we know them. So it would be useful, I think, to understand why water is considered a universal solvent. Even though it's not universal, it does dissolve a great many things. And in the process, we might understand something about those substances that it will not dissolve. And then there's a middle ground where we can induce water to be the solvent or dissolve things that are not normally soluble in water, but if we add some other component to water, we can make those insoluble substances soluble. And one example of that is soap, right? It used to be that soap was manufactured, well, in fact, it is still manufactured, by the reaction of fats, lard, for instance, with lye, sodium hydroxide. And when it does that, it breaks the fat molecule up into its pieces. And one of those pieces is a fatty acid. And the fatty acid has 2 characteristics. One part of the fatty acid molecule dissolves in water and the other part doesn't. So that other part that doesn't dissolve in water could dissolve in insoluble substances. And in fact, that's how you get your clothes clean, or how we used to. The chemistry of detergents has advanced quite a bit over the decades. So now we don't have to rely on soap, but we have various types of anionic and non-ionic surfactants. Things that will do the same thing as soap, but don't have some of the drawbacks. So let's understand why water behaves the way it does. Okay. Water is a polar molecule. What do we mean by polar? Well, the reference there and the analogy for polarity is directed toward magnets. Magnets have poles, we know. As a kid, I used to play with magnets, as most, I don't know about girls, but boys always do. And one type of magnet is a bar magnet, and it'll be marked on one end as S and the other end as N. North Pole, South Pole. And if you bring 2 magnets together, like that, and you line up the poles, they repel one another. Right? There's a repulsive force that moves them away from each other. But if you reverse the poles, and you say flip the magnet around, then you get an attraction. Sometimes a very strong attraction. And molecules can be visualized as polar, similar to a magnet, but for slightly different reasons. So when we talk about the polarity of a molecule, we're talking about electron distribution. So if a molecule has an uneven distribution of electron density, one side of the molecule has a gathering of electrons and the other side has a deficiency of electrons, you will produce a polar molecule. Right? So the way you do that is you need a molecule in which the attraction for electrons is stronger toward one atom than the other. So for each one of these bonds, we have an attraction of electrons toward the oxygen, away from the hydrogens. That's a water molecule. Well, that's the first requisite you have to have, is that uneven attraction. The other thing you have to have, because if we look at the molecule this way, then the attraction, this polarity, balances that one, and the whole molecule is nonpolar. So what you have to have is the right geometry. And in fact, the geometry for water is like this. So that attraction is generally directed the same way. So overall, the molecule is polar in that direction. Okay? So it's going to be slightly negative on this side and slightly positive on this side. Okay, that makes for a polar molecule. That's why we say the bent molecule in this case makes the difference. Okay, an unequal distribution of electrical charges. Now those are not complete charges, not like a sodium ion and a chloride ion coming together to form sodium chloride. In this case, you're talking about a molecule where the atoms are bound very tightly to one another, but the distribution is not equal in electron density. So you have slightly more electron density over here and less on this side. And that gives you a polar molecule. All right. So why does that matter? Well, as it turns out, water is not the only polar molecule in the universe. It's not the only thing that has a charge or even a partial charge like this little small d. That's the Greek delta. A small d is used to represent a slight charge, not a complete charge. In other words, the electrons are not transferred completely to that side of the molecule, just that they spend more time over there, which gives you a slight negative charge here and a slight positive charge over there around the hydrogens. So there are other substances in the universe that are polar or ionic, and they will attract if they're slightly positive in charge. That side of the molecule will be attracted to the negative side of the water molecule, and that attraction aids in pulling those substances into solution. So solutions tend to form in aqueous solution when they are polar molecules or ionic in nature. Now there's some ionic molecules, the ionic compounds, I should say, that form those precipitates. And in that case, you've got a competition of attractions between the ions of the compound and water. And if the force of attraction is much, much stronger for the ionic compound than it is for the water, then those ions will bound together, form the solid, and precipitate out of solution. So there's a competition going on there. If water wins, then you got a solution. If the ions win for the compound, then you have precipitate. But that explains why ionic substances tend to be dissolved in water, and non-ionic substances, for instance, oil, does not dissolve in water because it's non-polar. Here's an example. This is like a animation. If this is a sodium chloride crystal, right? You spill salt on the tabletop and take a magnifying glass, look at it. Those crystals are going to be little cubes. And that's because of the way that sodium and chloride come together to form the solid. They form a lattice with sodium surrounded by chlorides and chlorides surrounded by sodiums in every dimension. In this case, we're only looking at 2 dimensions, right? Sodium here against chloride, sodium, sodium, sodium. But you got to remember that sodium is also behind and in front of the chlorides. So each chloride is surrounded by 6 sodiums, and each sodium is surrounded by 6 chlorides. So we could write the compound that way, which would be more descriptive of what's actually happening in the crystal. But the convention is simplest whole number ratio, which is why we only write 1 and 1. Now, what happens when you drop a crystal of sodium chloride into water? Well, the sodiums are attracted to the negative side of the water molecule, like this, okay? And through a process we call hydration. So the sodium ions are hydrated, and the force of attraction between the water molecules and the sodium ion is very strong, but the water molecules surrounding sodium are also being attracted away from the crystal by other water molecules that are associated with, that are attaching themselves to this water and pulling it. So there's a lot of force involved to break that crystal apart. It's not just those 4 4 water molecules. Those water molecules are in turn being attracted by other water molecules that are pulling that crystal apart. Same thing happens for chlorides. Only this way, the positive side of the molecule is attracted to chlorine, or the chloride ion, and it's pulled away for similar reasons. And it just keeps going until the crystal is completely destroyed. Okay, so what happens when you do dissolve an ionic compound in water? Well, it's important to recognize that water is an insulator. In other words, it will not conduct electricity. Unless, of course, you get the voltage really high, like thousands of volts, 10, 20, 30,000, like you would see in a lightning strike. In that case, you're changing the character of the water. So we're not gonna focus on that one yet. So this low voltage situation, that looks like a 6-volt dry cell battery. And these electrodes submerged in water. And notice the light bulb does not light because water is an insulator. There's nothing ionic here that can carry the charge from one electrode to the other and complete the circuit, right? In electricity, unless you complete the circuit and allow electrons to move through the wire in a complete circle, then they're not going to move. But what happens when you put an ionic substance dissolved in water? Now you have mobile ions, and they will carry the current from one electrode to the other, and now the light bulb will light. That's characteristic of substances we call electrolytes. So if you get a doctor's report from your blood work or your urinalysis, it will include a series of ions in there called electrolytes. And they're just this. They form ions in water. They may include sodium, chloride, calcium, magnesium, potassium, are the major ones that you'll find in blood plasma. But that's what these ions do in solution. They make the water conductive of electricity. Now, if the substance completely dissociates and makes a lot of ions in solution, then it's known as a strong electrolyte, and you'll see a bright light bulb, lots of current flow. If it only partially dissociates in aqueous solution, then you have very few ions to transmit the charge, and in that case we have a weak electrolyte. Let's see, I thought they were going to mention weak electrolytes here. Okay. All right, it's being difficult. I wanted to go backwards, but it's not going to let me. All right, so here's the solution to that. Stop the share and restart the share. If I can remember where I put it. Here we go. No, sorry. I have to. Oh, I have to find the slides and go back manually. Let's see. Okay. Okay, now I can share once I fixed it. All right. So this is where we were. Okay. A weak electrolyte, example. All right, a strong electrolyte would be something like sodium chloride. It just completely dissociates. A weak electrolyte might be some form of weak acid, like acetic acid, right? Acetic acid is the component in vinegar that makes it sour, but it doesn't dissociate completely. In other words, it produces some of these and some of these. But it prefers, oops, wrong direction. It prefers to be in this form, the non-ionic form. Now, it's still soluble in water because that's a polar molecule. But once it goes into solution, it may dissociate partially and form a weak electrolyte, which would make a dim light bulb. All right. So this is an example of two solutions, potassium chromate. Now, that earlier picture that showed the yellow liquid being poured into the clear liquid, this is what that is. Potassium chromate is yellow in solution because of the chromate ion. Barium nitrate is colorless. And when you put them in solution, they break apart completely. Potassium, independent ions, chromate ions, independent, completely solvated by water molecules, surrounded by water molecules. They're in solution. Barium, similar, and nitrate. Barium and nitrate both go into solution But when you put them together, the force of attraction between a barium and a chromate is much, much stronger than the attraction that would pull them apart. So when you put them together, the barium and the chromate bind together and form a precipitate. Now, the solution is still, it continues to be conductive of electricity because you have spectator ions that are still in solution. The potassium and the nitrate are still in solution, and they will conduct electricity. But they will conduct electricity less efficiently because we removed some of the ions from solution. Okay, so how do you predict the products of this type of reaction? This is a type of reaction we call a double replacement. And in generic form, you would have the cation and anion, right, in aqueous solution. And then you would have a cation and another anion in aqueous solution, right? So that's the positive, that's the negative one, positive, negative one. They're in solution. So you have the opportunity to interact completely once you put the two solutions together. And what will happen is one will replace the other. Like this one will swap over here, this one will go over here, and now you have the AD and the CB. Cation, cation, anion, anion. Now, that predicts the possible outcome of the reaction, except we haven't said anything about solubility yet. So how do you know if it's soluble or insoluble? Well, there are a series of rules governing solubility that are generally true. But in this class, and in fact, all my chemistry classes, I don't expect you to memorize those rules. So what I've done is I've reproduced the rules plus added a chart. Right? So in this case, where we have potassium and nitrate together with barium chromate, you can form a grid and say, okay, what happens with potassium and nitrate when they interact? Right? What do you get? Well, you get a let's see, you get a soluble compound. What happens when potassium and chromate interact? Well, potassium chromate was the original solution, right? Originally, potassium chromate was in solution, so we know it's soluble. And barium nitrate was the original solution. We know it's soluble. But when you interact barium and chromate in solution, what happens to those two? Right? So barium chromate, we need to ask that question. Is it solid or is it aqueous? Right? So you look at what those interactions, possible interactions can be, and then you compare them to which is most likely the solid that's formed. Right? These are the reactants, right? We mentioned those earlier. They're aqueous solution. But when you combine the ions from those aqueous solutions, you may form different associations that are not soluble. So potassium nitrate, when it's not in solution, is a white solid. Barium chromate, when it's not in solution, when it's a solid, then it's yellow. So that's one indication. We would expect the solid to have been barium chromate. That's one clue. Another clue is to look at the rules, right? So we know that all nitrates are soluble, right? Barium nitrate, potassium nitrate, they're soluble. Most salts form from sodium, potassium, and ammonium, right? That's one of your polyatomic ions. They're also soluble. There are a few exceptions, but most of them are soluble. Most chlorides are soluble, with exceptions. Silver chloride, a lead 2, right, 2+ charge. Lead 2 is insoluble. Silver chloride is insoluble. And mercury, that's mercury 1. How do I know that? Because chloride is always -1. So that means you have 2 minus here. Right? Total, 2 times -1. So that means this group has to balance with a 2+. Well, you've got 2 of them. So each one would be a 1+. So that's why I can say that it's mercury 1. Mercury 1 chloride is insoluble. Most sulfates are soluble, SO4, the polyatomic ion, except for barium sulfate, lead 2 sulfate, and calcium sulfate. Those are insoluble. Most hydroxides are only slightly soluble, and for our purposes, we would classify them as insoluble. With exceptions, sodium hydroxide, potassium hydroxide are soluble. Barium hydroxide and calcium hydroxide are moderately soluble. Right. So what are we saying? We're saying that solubility is relative. When you say something is insoluble, in fact, it may only be slightly soluble. Most of it forms the solid. But in fact, all solids that are classified as insoluble are slightly soluble to a certain extent. It may be just the minutest amount of solubility. So at this point, we're trying to differentiate between solid and soluble and insoluble, and we'll deal with the middle ground later. Most sulfides, carbonates, right? Sulfides, carbonates, phosphates are only slightly soluble, which in our world now would be insoluble. All right, so here's the solution to that problem I've devised. Well, actually, I found this chart and made a copy. If you look at the cations across the top, find your cation, and go down until you find the anion that is part of the compound. And if the block is clear, then they're soluble. The compound is soluble. So for instance, potassium. Here's potassium, and we follow it down to nitrate, which is the first one. That's soluble. If we take barium and follow it down till we reach chromate, right here, right, there's chromate, there's barium. That block is grayed out. That means it's insoluble. Okay, so this way, and this chart is available in useful information in the review document, and it will also be available for the exam. So you don't have to memorize those rules. If you use it enough, then the rules become familiar. But I'm not trying to turn you guys into chemists. So I'm not going to have you memorize these things like I had to do when I was in school. Just learn how to use this chart. And you can judge from here whether it's soluble or insoluble. Okay. So these are reactions in which a solid forms. Using the solubility rules, you can predict a soluble solid. And one thing about those rules is they're set up in order. 1, 2, 3, 4, 5, 6. So that if you have a situation where you have a tie, you've got one situation, say with number 5, versus another situation that it also satisfies number 1, the number 1 wins. Right? So if it's a battle between 1 and something below it, 1 wins. That means it's soluble, because all nitrate salts are soluble. And we're saying salts here in the chemical generic term, not table salt like sodium chloride. That's a salt, yes, but it's also a chemical salt, and there are a whole host of other compounds that satisfy the definition of chemical salt. And they're all ionic compounds. Okay. All right. So, in order to predict whether or not you have a solid formed from a chemical reaction as a precipitate, you write the reactants correctly, and then you do that double replacement. And you see whether that rearrangement of ions produces a soluble compound or an insoluble compound from your chart. Now, there are cases in which you can put more than 2 reactants together and get a rearrangement of ions that'll produce a solid. So if you have, say, 3 compounds together in a solution and you want to see which is solid, all you have to do is take those 3 solids, 3 solutions, and you can form that grid and say these are the cations and these are the anions, and cross them and see what possible combinations you can have. So it doesn't have to be just a double replacement. It could be multiple replacements, and see which combination of ions produces the solid. If there is no solid produced, then you don't have a reaction. Okay, let's see if we have gathered anything from this discussion that can help us answer a question. Which of the following ions form compounds with lead 2+ that are generally soluble in water? Right, so we have these possibilities: sulfide, chloride, nitrate, sulfate, and sodium. Okay, test-taking technique. Eliminate the obvious stupid answers, I would say. 2 cations do not form a compound. Sodium does not react. Sodium 1+ does not react with lead 2+. Right? You need an anion. So we can eliminate E right off the bat. Then you look at the other possible combination: lead sulfide, lead chloride, lead nitrate, lead sulfate. Which ones are generally soluble in water? Well, you can look at your chart and find that the sulfides are insoluble. The chlorides for lead are insoluble. Most chlorides are soluble, but not for lead. Nitrates. All right, that's rule number 1. All nitrates are soluble. I can't think of a single exception. So that one is going to be a soluble. The sulfate is insoluble. And you can just check it with your chart. Okay, sodium phosphate solution reacts with lead 2 nitrate. What precipitate, if any, forms? All right, this is a word problem. So since we're not asked to generate a balanced equation, really all you have to do is just say, what are the ions, right? Sodium phosphate. So you've got sodium here, and you got phosphate here, right? And then you have lead 2 nitrate. So you have lead 2 here, and you have nitrate here. Just like in the chart. And then you say, what do you get here? Sodium phosphate? You look it up. All sodium salts are soluble, right? So that one's soluble. Now let's be consistent. That looks too much like solid. So let's say, there we go. Aqueous solution. How about lead phosphate? Look that one up. That's insoluble. Sodium nitrate. Sodium salts and nitrate salts are all soluble, so that's a double whammy. And lead and nitrate. That's also soluble. So what will form? The combination of lead and phosphate. Now, if you're asked to write the compound, you need to balance charges within the compound. So what we would have would be the lead and the phosphate. Right, you're going to need 2 of these and 3 of those. Right, that cross multiply trick. 3 over here, 2 over there. And that gives you 6 pluses and 6 minuses. So that would be your insoluble compound. Right there. Okay? All right. What's next? Oh, another concept. Consider a solution with the following ions present. Okay. So those are your ions. What's the question? When all are allowed to react, that is, they're all in solution together, how many different solids will form? All right. So let's set up our grid, right? Cations across the top, just like our solubility chart, anions down the left-hand side, and see which combinations produce precipitates, right? So we have a lead 2 plus first. Next is potassium. Then silver. And those are all the cations. Now we put the anions down the left-hand side. Nitrates. And chlorides. Sulfates. And phosphates. Okay? So then we just make combinations and see which ones are aqueous and which ones are solids, insoluble. Right? How about lead nitrate? All nitrates are soluble. Okay? How about chloride? Lead 2 chloride forms a solid. Potassium chloride is aqueous. Right? Potassium salts are soluble. Chloride, most chloride salts are soluble. Silver chloride, that's one of those exceptions, forms a solid. How about sulfate? Lead sulfate is insoluble. Potassium sulfate is soluble. Silver sulfate, I'm not sure about that one. Let me see if I can read my hard copy here. Where's silver? There it is. Ah, insoluble. Okay. Lead phosphate, that's insoluble. Potassium phosphate is soluble because it's potassium salt. And silver phosphate is probably insoluble. Yep. All right. So there we have this one, these 2, and these 2. Now let's see if this agrees. Now it says 5 solids. I picked out 6 solids. It says lead chloride Lead 2 chloride. Okay, we got that one. Lead sulfate. Got that one. Lead phosphate. Got that one. Silver chloride. Got that one. Silver phosphate. Got that one. It doesn't list silver sulfate. On the chart, it's insoluble, right? So that's an error in the slide. This one should also be insoluble. All right. So when we write these equations, notice that in order for the reaction to occur, we form a solid. If you don't form a solid, then you get the same ions, all the same ions floating in solution. It's like they're just in solution and they're not doing anything, right? So the driving force for this reaction is the formation of that solid. Well, that's really an advantage. If you're going to have a reaction and it forms a solid from free ions in solution, then we can say some things about that that may be useful when we go to prepare those solutions and present that reaction in a lab exercise, for instance. All right, so here's a reaction where you have potassium chromate, barium nitrate forms barium chromate and potassium nitrate. And the solid here formed, barium chromate, is the driving force for this reaction. So how would we write that? Well, you can write it in three different forms. The first form is called the molecular equation. And that's where you assume that these are compounds, even in solution. Now, we know they're not. If they're aqueous solution, then the ions are separate. But sometimes it's easier to balance the equations if you write them as if they were whole compounds and just say they're in solution, right? So that's what this molecular equation looks like. But like I said, it doesn't give a very clear picture of what's actually happening in solution. To do that, we have to break the ions apart. Right? So we take this compound and break it apart into its individual ions. So if this compound has 2 potassiums in it, then as free ions, it's going to have a coefficient of 2 in front of the potassium. And this one, there's only 1 chromate in that compound, so there's only 1. Barium nitrate, similarly, there's only 1 barium, 2+, but there are 2 nitrates because they have this parentheses with a subscript of 2. So you have a coefficient of 2. Then you do the same thing for the products. You have the potassium left over and you have the nitrate ions left over, right? Same number on either side, potassium on both sides, nitrate on both sides, and the solid. Now this is a bona fide solid that you cannot break apart. That's why the parenthetical S means it's a solid, so it has to stay that way in this form, which is called the complete ionic equation. This is what's actually going on in solution. Okay. Notice, I mentioned earlier, you got the same number of potassiums on both sides of the equation. So in mathematics and chemistry alike, if you got the same terms on both sides in equal amounts, they cancel. It's like they're not even there. In chemistry, we call them spectators. They're just there watching the show. And if we eliminate those spectators, then this is what we have left over. Eliminate the nitrates and the potassiums on both sides. And this is really the meat of the reaction. Barium ions combining with chromate ions to produce barium chromate solid. That's known as the Net Ionic Equation. Now, what value is that? Well, as a practical application of the Net Ionic Equation is, suppose you want to carry on, you want to produce this product, but you don't have potassium chromate in your lab. So you have sodium chromate. Use the same concentration, molar concentration of these, of the sodium chromate in solution with the barium nitrate, and you get the exact same net ionic equation. You will produce this solid just as efficiently as potassium nitrate, or potassium chromate, excuse me. Okay, so that's one application. This is really what we're focusing on, so this doesn't matter what the counter ions are. That's what we call them. The spectators are the counter ions that can be eliminated in the net ionic equation. Okay, so let's say we have this, we want to use what we've learned and take this reaction here. We're only given the reactants, and this is the one time when it's fair to give you only the reactants and let you figure out what the products are. Most of the time we say exactly what the products are, and then you take it from there. But in this double replacement ion swapping scenario, it should be fairly simple to determine what the products are. So we have a reaction of cobalt-2 chloride. In aqueous solution, right? And we need 2 of these. Why? Because the cobalt is 2+. Says so right there in the name. Chlorides are always -1. So that's one reactant. The other reactant is sodium hydroxide. You know, I'm going to run out of room. I better rewrite these. Let's do this. Cobalt-2 chloride plus sodium hydroxide. Okay. Now, what does that yield? Double replacement. We swap this cation for that cation. So this now becomes sodium chloride, which is soluble, and cobalt hydroxide, which is a solid. Just look it up in your table. Just look it up in your table, find cobalt. Let's see, I think that's copper. Where's cobalt? Maybe that is cobalt. No, I think it's copper. There's no cobalt in here. All right, so we have to assume that they know what they're talking about. Let me take this. Hold on a second. Hello? Yes. Uh-huh. Okay. What day of the week? Let me see. March the 3rd at what time? 11:30. Yeah, I can make that. Okay, I'm going to make a quick note. March the 3rd at 11:30. Okay. All right. Okay, bye-bye. Sorry about that. When a doctor calls, I have to answer. Okay, back to our equation. The rules state that hydroxides most hydroxides are only slightly soluble, right? So this is not one of those exceptions, so we can assume from the rule that this is insoluble. Now, we need to balance the molecular equation. This is the molecular equation. All right. So remember that trick. If you have polyatomics on both sides and they're not broken up in the process, you can use them as balancing. And the nice thing about these double replacement reactions is usually they balance really simply, really easily. So with a little practice, you don't even need to use the budget anymore. You can just say, all right, I've got 2 hydroxides over here, I need 2 here. That means 2 sodiums here, 2 sodiums there, 2 chlorides, 2 chlorides, and you're balanced. Right, so that's the balanced molecular equation. The complete ionic equation then, and you have to do the molecular first, because that tells you how many ions of each one are going to be in solution. So this one in solution produces cobalt 2+ plus 2 chlorides, right, because of that subscript. Then you have 2 sodiums plus 2 hydroxyls. All right. Now on this side, you have 2, I'm going to come down here. You have 2 sodiums, products, 2 chlorides, product, and you still have your solid cobalt 2 hydroxide. Remember, we can't break that one apart. It's a solid. That's your complete ionic equation. Now to form the net ionic equation, we eliminate the spectators. So the spectators are chloride, chloride, sodium, sodium. And now our net ionic equation is the cobalt in solution reacting with hydroxide in solution to yield cobalt solid. That's the net ionic equation. Right? Okay. So you should be able to do that. I mean, since these things balance so easily, the real focus should be on getting it balanced correctly as a molecular and then migrating to complete ionic and then to net ionic. Okay. I know we haven't talked about acids and bases in this format. At least I don't believe we have. Make a quick look. Yeah. Chapter 16, we get into acids and bases. So this reference to Arrhenius acids and bases won't mean anything to you. So just hold that in reserve. And when we talk about the reaction of acids and bases, this is what an acid looks like. It has this proton in front, right? And we get that from naming convention that we've already covered, right? You have that proton in front that can dissociate. So when you put it in water, the proton comes apart and leaves the counter ion, in this case chloride. In this case, it's nitrate, a polyatomic. In this case, it's hydrogen sulfide. Hydrogen sulfate is the polyatomic. And you have this free proton floating around. Now, that's a strong acid, which completely dissociates at least one proton. Hydrochloric acid, for instance, in this case, looks like that. So you have these separate ions floating around in solution. Similarly, for bases, right? For this type of base where you have the hydroxyl as part of the molecule, it will dissociate into sodium and hydroxide, the potassium and hydroxide ions. So when you put an acid and a base together in aqueous solution, where you just combine them, what are they going to do? Well, I'll show you. See, am I still drifting a little bit? There we go. So whenever you combine an acid with a base, you get two products. You get a salt and water. Right? That's common to all acid-base reactions. So the acid has that proton, right? And the base has the hydroxyl. Right? So it's a generic, right? There's the proton, there's the hydroxyl. The salt is the combination of these two, the cation and the anion. That's the chemical definition of a salt. The product of an acid-base reaction produces a salt and water. And the water forms from these two components right here. So obviously you need two hydrogens, so you would have to do like that if this was only one. Well, actually, you don't have to do that. I'm sorry. There's a hydrogen, there's an oxygen. So that's balanced as written. All right. So the salt is an ionic compound, and it could be soluble or it could be insoluble. Right? You don't know until you actually are given the exact reactants, and you're able to judge whether the product, the salt product, is soluble or insoluble. But the net ionic equation for every acid-base reaction, and that's also misleading, because, for example, if you have hydrochloric acid and sodium hydroxide, what salt forms from that? Well, what we normally think of as salt. But is it soluble? Yes, it is, plus water. So for this reaction, yes, the spectators are those two ions because they're still soluble on both sides. So you have this one plus this one yields water. That's the net ionic equation in that case. But if you have an acid and a base reacting and they produce a salt that's insoluble, which is rare, then you could conceivably have a net ionic equation that's the same as the complete ionic equation. Because if you form a solid in this reaction, then you don't have any spectators to cancel. But for all intents and purposes, at least for this course, the net ionic equation for an acid-base reaction is proton plus hydroxyl yields water. Okay. Let's see. Those are common strong acids: hydrochloric, nitric, sulfuric. They completely dissociate. Now, when you have a diprotic or a triprotic acid, the complete dissociation is only for the first proton. And I'll explain that later. When we get to acids and bases, I'll explain why that happens. But for our discussion now, it's a strong base because that first proton completely leaves. It's gone. It's in solution, separate from the HSO4 minus 1. A strong base, on the other hand, produces a complete dissociation of the cation and the hydroxyl. And like I said, for our purposes, the net ionic equation for this reaction is always proton plus hydroxyl yields water. And that should also always be the case for strong acid, strong base reactions. When you get into weak acids or weak bases, then you have a slight modification to the approach. Okay. So the net ionic equation for this reaction, recognize that it's an acid and a base, is C. Right, that's your net ionic equation. So if all you're interested in is the reaction itself, then it doesn't matter what the acid or the base is. You still get the same product as water. Now, other types of reactions. Those were acid-base reactions. The oxidation reduction reaction refers to a transfer of electrons. Now, for these authors in an introductory course, the easiest way to wrap your mind around this transfer of electrons is say it's always a metal and a non-metal reacting. But the fact is that oxidation reduction reactions can occur between two nonmetals. And they do. Not just can, they do. But to illustrate the point, what we're seeing here is a transfer of electrons from magnesium to oxygen. Magnesium is the metal, oxygen is the nonmetal. And when you do that, you produce ions that then attract one another. And that's your electrostatic attraction that produces ionic compounds. Okay, so if we take this as an example, we have magnesium metal and oxygen non-metal, it's a gas, and it produces magnesium oxide, solid. Okay, so the way I like to do these, once you write that out, the way I like to keep track of my electrons is just draw lines. So to go from here to here, what was the charge here? The charge here is 0, right? Completely balanced with electrons. Over here is a 2+. So what has occurred between here and here? You've lost 2 electrons. And that's for each magnesium. I do it that way because sometimes you have more than one. And we're talking right now about each individual atom of magnesium. In this case, there's still 1 on both sides, so it doesn't matter. But this is not balanced either, is it? There's 1 oxygen here and 2 there. So I'm actually, at this time, I'm showing you a procedure for balancing equations that have transfers of electron. So from this oxygen, which is also a 0 charge, what has happened? Well, this is a 2-, is it not? So that means oxygen has gained 2 electrons per oxygen atom. Okay? Now, at this point, that's okay. But we're not balanced, right? So how do you balance this? Well, you do have 2 oxygens here. So that means if each oxygen lost 2 electrons, gained 2 electrons, excuse me, that means overall there were 4 electrons gained. But you need 4 electrons over here, and you've only got 2. So how do you get 4? You multiply this by 2, right? And you have to use that coefficient because this is a compound. So 2 oxygens now makes that 4, but this makes that one lost 4, right? So if you lost 4 electrons, how did you get there? Well, you had to multiply by 2, which means this has to be also 2. So that's how we balanced our equation, using a transfer of electrons to track the changes. And in this type of reaction, the number of electrons transferred, lost, has to equal the number gained, always. Okay, so why do we call it oxidation reduction? Well, it's the name that's assigned to each one of these processes. If the electrons are lost, then that's a process of oxidation. And if electrons are gained, that process is called reduction. Okay? Just memorize it. Oxidation. I got an acronym. No, a mnemonic. Excuse me. A mnemonic to help you remember. Oil rig. Oxidation is loss. Reduction is gain. Okay? Oil rig if you have trouble remembering it. All right. So the key to this type of reaction is that electrons have been transferred. Now, there's also a shortcut, a rule of thumb, if you're only interested in what type of reaction is it. If you have an element on one side, either as a reactant or a product, and then on the opposite side, it's part of a compound, then it's always oxidation reduction, or redox for short. redox reaction. So if you have an element here, and it's in a compound on this side, on opposite sides, that's oxidation reduction, redox. Could go the other way, right? So it's just which is opposite sides. In this case, right, we have free aluminum metal, and as a product, we have iron metal. The other reactant on this side is iron 3 oxide, and then the product on this side is aluminum oxide. Notice that aluminum is an element on this side, and in a compound on that side, this is a redox reaction. Electrons have been transferred. And in this case, the electrons were transferred from the aluminum to the iron, which made the iron 0 now charge and made the aluminum 3+ charge. Okay, actually this is a special type of reaction that's still used today in the railroad industry. When two rails are being permanently joined, then this reaction is often used. It's called thermite. It forms at extremely high temperature and in the process produces iron. So the actual weld joint that's formed from thermite reaction on a rail line, the weld joint is stronger than the rest of the rail. All you have to do is, after you finish the reaction, is go in there with your grinders and make it smooth all around, so your wheels don't hit bumps every time they hit a joint. Now, it used to be we couldn't do that. You couldn't join two rails because the coefficient of expansion was too great. In other words, as the temperature changed outside, then the rails would do this thing, right? They changed length. So they always had, when they were joined together with the bolts and the brackets, there was always a gap. So there was room for expansion and contraction. But now we've got low expansion steel that's used in the rail lines, and you can join lines that are several miles long and they won't significantly expand or contract, which makes for a smoother ride, because every time your wheel hits that joint, there's the risk of damaging the wheel and the rail too. So a smooth rail is better than a bumpy rail. Thermanite charges were also taken into battle during World War II. When our troops landed in Normandy, they had, I don't know if they were frontline troops or follow-on troops, but what they would do was, once they had taken over a gun emplacement from the Germans, they would take these thermite satchels and they would put them either in the barrel of the gun or in its mechanism, set them off, and they would just weld the gun shut. It couldn't be used again. So that was one way to keep the Germans from coming back and turning the guns on you. You just throw some thermite on it and forget about it. Okay, so in this case, we see that aluminum has lost 3 electrons and each iron has gained 3 electrons. So that's really a one-to-one exchange. And nothing happened to the oxygen, right? Oxygen did not change at all. It stayed 2- through the whole process. So in one respect, it was just a spectator. Okay, that's true. When you have a metal and a non-metal together, you can assume that it's an oxidation reduction reaction. That's true. And this is an added statement that I've given you already. Two nonmetals can also undergo oxidation reduction. Now, I'm not so sure about this looking for oxygen as a reactant or a product, because it doesn't have to be oxygen as the nonmetal. For instance, okay, in your automobile exhaust, very often oxides of nitrogen are produced. Could be this one, could be this one or the other. We'll just pick one. Let's just say it's this one. So what we want to do is, in the catalytic converter, we want to produce nitrogen gas. Because that's non-reactive. This is a reactive molecule. But in this case, the oxygen is 2 minus. That means the nitrogen is 2 plus. So what we need to do is add 2 electrons to that nitrogen so we can get it to be like that. Well, one possibility is to take unconsumed, in other words, extra oxygen that's in the exhaust flow, and there'll be plenty there, and transfer some electrons from this oxygen over here. So that takes place in your catalytic converter. I'm not going to give you the full equation because I can't remember it. I was just trying to illustrate the nonmetals can also be, a better example would be this. Right? 2 nonmetals, both gases here, and that room temperature liquid here. These are 0, no charge, right? And if we transfer electrons from here to here, so this would be 2 electrons per oxygen, then you would end up over here with a +1 and a 2 minus. Okay, so you would need these 2 hydrogens. Actually, you'd need more than that, because if this is a 2 minus over here, then for these 2, you would have times 2 would equal 4 electrons for the total. So that means 4 electrons from here, since only 1 electron can come from each hydrogen, right? It's 1 proton, 1 electron, that's all it has. Then you would need 2 of these to transfer that many electrons. And that means that you would also need 2 over here, because you have 2 there and 2 there to make the charges balance. So that was 2 nonmetals. Now, I told you that these were charges, but they're not really charges. We're using a bookkeeping scheme called oxidation state. We are not arbitrarily, we are assigning charge, but it's not really charge, it's an oxidation state. And it's just a way of keeping track of electrons. Now, if there are ions in there, the oxidation state and the ion charge, they're equal. But in these cases, the oxidation state here is 0. The oxidation state here is 2 minus, but this is a compound that's not ionic. So we can't legally say that these are charges. Okay, so we've looked at these driving forces for reactions, right? Precipitation is one of them, forming a solid. Acid-base reactions, right? Formation of water. Now, the formation of water doesn't have to be an acid-base reaction. It can occur from other sources, but most of the reactions that form water are acid-base. Oxidation reduction reactions, redox, transfer of electrons, those drive reactions. Formation of a gas. Now, in this case, you've got zinc metal here that ends up in a compound over here, right? That is a redox reaction. So the transfer of electrons and the formation of a gas are driving forces here. And so you don't have to just have one driving force. You can have multiple forces. One is the formation of gas, one is the transfer of electrons. Both combined makes for a pretty convincing chemical reaction. This is often called a single replacement. Why is that? Well, you look here. Zinc is actually replacing that hydrogen. So that over here you have zinc and chlorine together. And here you have the displaced element forming the gas. That's a single replacement. This is a schematic. Chemical reaction can either be a precipitation, right? Or it could be an acid-base reaction. Or it could be an oxidation reduction reaction. And a subcategory of oxidation reduction reactions is combustions. So in order to have a combustion reaction, you've got to have oxygen. Elemental oxygen on the reactant side means that you have a combustion. But you've also got an oxidation reduction reaction, right? Because you've got an element here and it's in a compound over here and here. Okay? So like I said, they can be multiple examples in one reaction. All right, we have other names that can be applied to reaction. A synthesis reaction or a combination takes simple and makes complex. And the best illustration of that is two elements combined to form a compound. That's a synthesis. It's also a redox reaction. And this is also a combustion reaction, right? You got all three of those types describe this same reaction. A decomposition goes the other direction. It takes complex and makes simple, right? So electrolysis of water would be an example. You run a direct current through water. Of course, water has to have a little bit of something else in it to make it conductive. So we just use a few drops of acid, hydrochloric acid, makes it conduct electricity. And in that case, you break these bonds and form these individual elements. And that decomposition reaction is also a redox reaction because you've got elements over here from a compound. So we can expand our chart further. So these oxidation reduction reactions could be combustions, they could be synthesis, they could be decomposition. So what type is this? Well, it's oxidation reduction, right? Elements to compound. Oxygen is involved. It's a combustion reaction. In fact, it's a very violent combustion reaction. That's the one that we use in many of our rockets these days. For engineering reasons as well as for chemical reasons, this reaction is very efficient and it produces what the rocket engineers called high impulse. In other words, you get a lot of push from a little bit of compound, or a little bit of reactants. That means your rocket, you can put more payload on there with less fuel because the fuel is more efficient. That's why hydrogen and oxygen are an ideal propellant and oxidizer combination. So they're all the above. Oxidation, reduction, combustion. I left out synthesis. Simple to complex. So all three of those apply to this reaction. All right. So that's it for the slides. I was looking at when you begin to do balancing, do some more balancing of equations. The let's see. Well, that's not a good example. Let's classify some reactions. I'm going to dig into your review document and pull out some of these. And let's see, where would that be? Hold on a second. Okay. All right. So let's look at this one. All right. What type of reaction is that? Look at the reactants. What do we have? An acid, right? With a hydrogen in the front. That indicates it's an acid. When it goes into solution, that hydrogen dissociates from the nitrate. Over here we have a hydroxyl. That's a base. So we have an acid-base reaction producing a salt, combination of this anion and that cation, plus water. So that's an acid-base reaction. See, I'm sliding again, I think. There we go. Oh, sure. All right. Let's see. Let me pick. How about this one? What type of reaction is that? Well, you've got a decomposition, right? You're taking a complex, making a simple. you also have elements in a compound becoming free elements. Oxidation reduction. You have two types there. By the way, Ga is gallium. I don't think I had you remember that one, memorize that one. Let's see. How about this one? We may have already looked at this one on the slide. CO2 gas formed from carbon and oxygen. All right, so we've got elements over here and a compound there. That's a redox. Okay. And we've got oxygen. That's a combustion. And we've got simple to complex. That's a combination or a synthesis reaction. All three of those are possibilities. Okay, how about trying to find a good one. Yeah, I'm no good candidates right now. I'm going to let you work on those at your own pace. I was hoping to show you a balancing procedure that used redox to help, but I don't find one that's really good to do that in here. And that's, I mean, it's not necessarily bad, because that type of balancing is best left to a discussion of, a complete discussion of redox reactions. And I'm going to check to see if we're going to get into that. Yeah, the last chapter, chapter 18, when we talk about electrochemistry, then we'll look at redox reactions in more detail. Okay. Well, finished a little early.